Okay, so today we're going to talk about material selection for combined loading. So where we finish off, this is our element A. All right, this is our element A. Just to quickly recap. So on the last lecture, we analyzed a structure like this. Okay, so this structure have 4 different forces, have a very specific cross section that was selected, and then we're going to find now what are the stresses that is acting on this element at position A and at position B. Now this is for practice sake that we require you to calculate position A and B. In real life, where the structure will fail at here or at here at the bottom end. Okay, so this is just for practice. We want to calculate at element A, element B, what are the stress state. So where we finish off on Tuesday, we realized that our element has loading in both normal stress and shearing stress. Okay, and then most of the material behavior or material properties are measured in unidirection. Okay, unidirection means they are measured in one direction. Why one direction is easy to carry out? Okay, it's easy to carry out. It's very convenient to do. So there's only we only do tests ideally in either tension, uniaxial tension, or uniaxial compression, or unidirectional shearing stress. Okay, to do a test that is combined loading, like what you see, this is combined loading. Okay, to do a test that's combined loading, it's very expensive. Okay, it's not practical because under combined loading, then we have a state exactly the same like our element, which we have a tensile load and a torsion. Okay, so the question now is how are we going to select our material? Okay, so the only way to do this is to calculate the principal stress acting on the element. Okay, we have to calculate the principal stress acting on the element. So I realize quite a few of you have not remember or have not heard of Mohr circle. I'm going to do Mohr circle. Okay, but I'm going to show you how this is analyzed first. Okay, now the next part of the question is why. Okay, why principal stress? Okay. Why principal? Okay, why principal stress? I'm trying to figure out now. Did I got the word principal wrong? Okay, is it principal or principal? Anyone? I'm trying to look for my textbook now, and this is this is embarrassing. Where is my textbook? And somehow my textbook has gone missing.
It's principal.
So I got the right spelling, right?
Yes.
Okay, thank you. Right. So why principal stresses? Okay, why principal stress? Because in principal stress, because why principal? So principal stress okay has 0 shearing stress. Okay, so principal stress has what? 0 shearing stress. Okay, so somehow we're going to find the principal stress of this element. Okay, so it has zero shearing stress. And why is this zero shearing stress important? So if we were to focus on the material behavior, so let's say we are going to focus on the tensile, okay, tensile. So when we do the tensile test, right, when we do the tensile test, we have our element. So if we draw our element, right, the element, if I were to draw this and I will have, this is my X and this is my Y, the element is loaded in this direction in stress X only. Okay, the element is loaded in stress. So I wanted to put this aside first, okay, to see experimentally what do we get. Okay, so now based on our problem, okay, based on the stress we have, I'm going to draw this in 2D now. Okay, so in 2D, so I'm going to follow our transformation. This is our X and this is our Z. Okay, so I'm going to draw in 2D now. So this is our element. Okay, and then we will have our tensile stress. So this is reading at what 28.852. And then we have a shearing component, and this is sitting at 1.607. Okay, so 1 megapascal. Okay, so we have our, so I'm going to label, so I'm going to construct Mohr circle. Okay, don't worry about it, I'll go into more detail about Mohr circle, but I want you to see how is it done. Okay, so when constructing Mohr circle, we call this X, point X. Okay, hold on, we call this point X, right, because it's the plane intersecting the x-axis. And over here, this is our point Z. Okay, so this point X and point Z that I've drawn on the surface will correspond to point X and point Z on Mohr circle. Okay, I'll elaborate what do I mean by that. Right. So I'm going to construct. So this is our, this element is from the combined loading. Okay, so we're going to deal with this. Then after that, we're going to relate. Okay, after that, we're going to relate with material property. Okay, so after that, on the right hand side, we're going to relate to material mechanical properties. Okay, so take note, our material mechanical properties has only what, one direction. Okay, and it's in tensile mode because we are going to use this value. Okay, we're going to use this value. So by looking at our element, it is under, so what we call this is, we call this an element. Okay, we call this an element. So now we're going to construct Mohr circle. Okay, we're going to construct Mohr circle. So we're going to do Mohr circle. So we have 28 in tensile. Okay, so on Mohr circle, let me introduce you to Mohr circle first. So in Mohr circle, our x-axis, okay, the axis that you see down here that I'm drawing, is your normal stresses. Okay, so anything in that direction is known as your normal stress. So I'm going to call this my 0. Okay, so 0, 2, 4, 6, 8. So this is my 10, 2, 4, 6, 8. And this is my 20. Okay, I'm going to stretch it out. and this is my 30. Okay, so this is my normal stress, and then on my left hand side from the 0, right, like anything else over here, this will be my minus 10. Okay, my minus 10. So on the x-axis is your normal stress. On your y-axis, that you see over here, is your shearing stress. Okay, shearing stress. So this will be, so the stresses on your normal stress, the scale used for your normal stress and the shearing stress has to be the same. I repeat again, the scale that we use for our normal stress and shearing stress has to be the same. If you use differently, you will not get a circle. You get an over. Okay, so it's no more Mohr circle. It's known as Mohr over. Okay, so I'm trying to get rid of this. I'm using the wrong scale. So 1, 2, 3, 4, 5. So this is my 10. Okay, then down here 2, 4, 5. This will be my minus 10. Right. So on Mohr circle, the vertical scale is shear, and the shear will generate over here. It will generate a clockwise rotation. Okay, this arrow means clockwise rotation of the element, and then the one below will be anti-clockwise rotation of the element. I will elaborate later. Okay, but I want you to take note. So this is what Mohr circle is. Okay, on Mohr circle, the x-axis is your normal stress. So positive means it's going through tension. Negative means it's going through what? Compression. Okay, so we are going to have, so over here we can see that stress x is equal to 0. There's no stresses acting on the x-axis or stress in the x direction. Stress z is equal to 28.852, okay, megapascal. So this is positive, right? So positive. And then your shear xz is equal to shear zx, and this will be equal to minus 1.607 megapascal. So in this direction, I will elaborate later, okay? It's what we call negative shear. Okay, it's what we call negative shear. So from here, we're going to construct Mohr circle. So we know, wait, I think I should be okay. Yeah, I should be fine. So we are going to have two vertical lines. So we know that this is the 0 vertical is our stress X line. And our stress Z line is 28.852. So I'm going to eyeball this, okay? So 28. Okay, so this is, I know I'm not there yet. So this will be our 28.5. Okay, so this is your stress Z line. Okay, and then your shear is very small. It's 1.607. Okay, so this is, so your shear is 1.607. Now, I know that we have written negative shear down here, right? But you, on Mohr circle, you have to construct, you have to draw intersecting line on the positive and the negative shear. Okay, don't worry, I'll explain all this later on. So this is a shear. So positive shear. So 1.6 is about here. Then you have the other one. 1.6 is about here. Okay. So on the right hand side, you have stress X, Z, on your left hand side, right? So down here is your stress Z. The other side is stress X on the vertical because stress X has 0 normal stress. And your shear, I understand that we put minus, but we do both positive and negative. I can see that, okay? Now, let's look at where this X point is